Right, let's start. Okay, so we are studying various properties on this matrix operations, including matrix multiplication, addition, and scalar multiple, and matrix multiplication. Okay, then in this slide, it is discussing the matrix multiplication defined as AB. Okay, and in this case, considering this matrix as another matrix C, and then we can possibly think of like Cx is equal to D, or this kind of linear system, or y is equal to Cx as a linear transformation of any given input vector x, right? And so from this perspective of a linear transformation, where C is defined as A times B, we can we can roughly think of this mapping defined by Cx as ABX is A times bx first, right? So it's quite obvious. So in this case, we can think of like the first mapping defined by the matrix B. Okay, so the input vector x is first defined as another vector defined as b times x, and then further mapped or transformed by the matrix A, right? And so the final mapping can be defined in this form, and we can also view this mapping as first computing this A times B as the product of these two matrices, and then just a one-time linear transformation by the matrix C. Okay, so it is quite obvious. So in the previous case of passing through the first mapping of B and then A, that can be viewed as kind of composite function. So if you remember, like y is equal to 2x plus 3 and z is equal to maybe y squared plus 1, and then in this case so this is f of an x and this is g of an y, and then z is z is defined as g of f of an x, right? So this is called a composite function, and in Korean 이게 저기 뭐라고 그러죠? 합성함수죠? So we can define this 합성함수 or composite function in the context of a linear transformation by using this matrix multiplication. Okay. And now let's look into these two perspectives and then compare between them. And then in this case, let's consider this mapping of composite function. And then this guy, suppose B is maybe 1, 2, 3, 4, 5, 6. And then of course this vector x should be two-dimensional vector, right? And then we know that this guy is the linear combination of these two columns with respect to the linear combination coefficient of an x1 and x2, right? So we have seen many of these examples. So that way we can represent the first mapping output. Okay, and then this guy, okay, this guy is in this particular case, it will be some three-dimensional vector, right? And then the matrix A will be something like 1, 2, 3, 4, 5, 6, 7, 8. Oops, sorry. Yeah, let's consider this example where A is defined in this form. Okay, so in this case we can easily see that the mapping defined by B is taking the input of two-dimensional vector over here, right? So it's one vector in the two-dimensional space, and then this guy is three-dimensional space, and then this guy, yeah, after mapping through A, and then the final vector will be four-dimensional vector, right? But anyways, so this is our y, and then we will multiply the vector y on the right side of the matrix A, right? And then yeah, as a result we will obtain the four-dimensional vector. Yeah, so far is quite easy. Okay, and then from here we can represent first the linear combination of the columns of the matrix B, and then after multiplying A, and then we can just apply this distributive law, right? So A times maybe x plus y, which are the two different vectors, are, we can represent it in this form. So we apply that distributive law in this case, right? And then the next line is a little bit important. So here, let's look at this guy. Okay, so in this case, so we have A over here. So in this particular case, we have this 4 by 3 matrix. So, and then this will be our input vector over here, but this guy is not just the B1, but it's a scalar multiple of B1 with respect to the scaling factor of an x1. So here in this case, so we have x1 over here, and this guy is B1, and this guy is A, right? So this is describing the size of this product of matrix and scalar and vector, right? So in this case, if this guy is a scalar, and then we can freely move it out to the far left, the leftmost part. Okay, so in this case we can rewrite it into x1 and matrix A so this is an A and x it's B1, right? So it is saying that the scalar multiple, which is performed in the middle of these matrix and vector or matrix multiplication, it can be brought out to the left hand side, and then basically we can postpone the scalar multiple of this is product involving matrix and vectors. Okay. So in this case we can first compute this part, and then later on we can perform this scalar multiple. Okay, so that is described in this form. We just changed it to this form. Okay, but for here, compared to this example, let's consider some other examples of maybe some matrix multiplications of A, B, and C. Okay, so for example, this guy is a 3 by 2 and 2 by 5, and this guy 5 by 4. This is just one example. So in this particular case, it is normally not equal to like B and AC, right? So we cannot easily change the order of these matrix product, right? So at first the size doesn't even match, right? So this matrix multiplication is not even defined, right? But in this particular case, where we have the scalar in the middle of this product computation, and then we can move it to the left hand side, or we can basically place it anywhere in between this matrix product. Okay, so you can freely move to this side or this side, or stay over here. All right. And then this guy, if you look at this result, and then if we compute a and a times b1 and a times bp, and then we first compute this part, a times b1, and then this part will be just a 4-dimensional vector, right? And then this part is 4-dimensional vector, and this part is also a 4-dimensional vector. And then we can view this representation or expression as the linear combination of these 4-dimensional vectors with respect to these linear combination coefficient, right? And then now we can just assemble them into a these are the 4-dimensional vectors, okay? And then we aggregate or collect all these linear combination coefficients as a column vector, okay? So what from here here we can see that this guy, a times bx, or in general a bx as a composite function, can be viewed as we first compute this matrix multiplication, where that matrix multiplication a and b is represented in this form, and then once obtaining that matrix, and then we perform the linear combination of these columns by using the coefficient vector x, okay? And then how do we obtain, or let's look at this matrix, and then what is the what is the characteristic of this matrix? Okay, so it is just an intuitive understanding, or which is like each column of this matrix is the result of the mapping of the each column of matrix B, which are B1 through BP. Okay, so we first map each of these columns in B by using the transformation matrix of an A. Okay, so the matrix has that kind of characteristic. And so if you remember the linear transformation that we studied, which was like standard matrix. So standard matrix, do you remember that term? So so if you remember, like, so f of 10 is a 1, 2, 3, and f of 01 is 4, 5, 6, and then suppose this this transformation is linear, which is mapping the 2-dimensional vector into 3-dimensional vector. So in this case, how is our map transformation defined? It is defined as ax all the time. It is always defined in the form of matrix and vector multiplication, and we are just reviewing what we studied last time. And so what is an A? A is 1, 2, 3 and 4, 5, 6, right? And then x1 and x2. And what was the meaning of each of these two columns? So what forms the columns of our matrix? The first column is the mapping result or transformation output of the standard vector of 1, 0, right? And then this guy is the mapping output of 0, 1, right? But in this case of the composite function, each column can be viewed as like so in this case, so we have these two columns of B, 1, 3, 5, 2, 4, 6, okay? And then for each column that we have in our matrix B, we just compute its mapping through our matrix A. Okay, so that will form one particular column over here, and then we just concatenate. We aggregate these columns, which are output of these columns of a B through the mapping of A. Okay, so in the previous case where we saw over here, what was the function output, or what was the columns in our transformation matrix? That was the mapping output of the standard vector, unit vector 1 0 and 0 1 and so on. But instead, in this case, we actually compute the mapping of each column that we have in the previous matrix, or the matrix on the right, right? Does it make sense? Okay, so let me add a little bit more explanation that extends this perspective. So when looking at this transformation of Bx, okay, so what is the meaning of each column? So of course, each column is the function output of 1 0 and 0 1, right? And then what will be these columns in the total matrix as a single transformation perspective? So this guy is mapped to 135, right? And then 135 will be further mapped by A into this one, A and B1, right? And then we just simply list up these mapping. So from this perspective, okay, so we start with the 1 0, and then it is mapped into 135, right? And then it is further mapped by this transformation. So 135 is quite complicated, right? So let's just assume the result is maybe 11, 13, and 14, and 20, and it's just a random vector, but we assume it as a result of this matrix vector multiplication. Okay, so this unit vector is transformed into one vector in the middle space or intermediate space, and then it is further mapped by this guy, and then also we start with another vector, right, in the input domain, and then it will be mapped into 2, 4, 6, and then it will be mapped into some other 4-dimensional vector, and then we just simply concatenate them into a single matrix, and that will define just the one-time matrix transformation of this two-step composite function. All right, then then purely considering this product of the matrix, two matrices A and B, and then this A and B. Okay, so even before looking at the vector x, even before considering the vector x, then we can represent it in this form, and then B is basically composed of these columns, right? And then the resulting matrix of this AB is represented as A times B1 and A times B2 and so on, right? Right, and then also we can understand this relationship from the perspective of the column combination perspective of a matrix multiplication that we studied. Okay, so let's see. Okay, so if you remember this example, and this matrix vector multiplication can be viewed as a column combination, but what if we have this matrix and matrix as well? So applying the column combination perspective, we use this common set of these base vectors, and then the first column of the right matrix will provide its own linear combination coefficient, right? And then that way we form the first column, and then by using the second column as a new linear combination coefficient by using the same base vectors, and then we will form the second column, right? So that way this first column will only be used to determine the first column in the output, and the second column will determine only the second output, right? So columns are separated in this manner. So in this case, if we think of this matrix A as providing the base columns, and then from the column perspective, the B1, which is the first column of the right matrix, will provide the first set of the linear combination coefficient that will provide, or that will form, the first column, and then separately the second column of the right matrix will provide the new set of linear combination coefficients to combine those columns of an A to provide to form the second column, right? So that way we can understand this relationship as the column combination perspective. Okay. All right. So I'm gonna skip this example, and then row column rule for computing AB. So it is corresponding to the first perspective that we studied for this guy, matrix multiplication via this row and column combination, or the inner product perspective. Okay, so let me move to the second theorem. So it gives a bunch of different properties involved in this matrix multiplication, and so we have this associative law, and then distributive law, and then also another distributive law, and then scalar multiple can be freely moved, right, to any place. And then also this identity matrix, we also studied about this identity matrix, right? So whether it is multiplied on the right or left with the particular vector or the matrix, it will not change the original vector or matrix at all, right? So that is the property of this identity matrix. Okay, then so I will skip this proof of this associative law, and then we also studied that, or discussed about this commutative law is not satisfied for the matrix multiplication. And also we know, we understand this is not true. I mean, this is not equal to each other. And at the same time, another interesting property about this matrix multiplication is that suppose we have this relationship or this expression, and we cannot easily cancel out A. So in this case, we cannot divide the matrix multiplication by some matrix. Okay, so there is no notion of dividing by matrix, okay, because matrix is a two-dimensional array of numbers, right? So it doesn't make sense to divide some representation or expression by these two-dimensional array of the numbers. Okay, so in this case, we cannot cancel out the matrix A. Okay, so that way we cannot conclude B is equal to C. Okay, but we will see the case where this guy is true, okay, or the condition that this relationship is satisfied. So in other words, if this guy is true, and then this guy is also true, and when is this kind of relationship true? I mean, that's only when the matrix A is invariable matrix. Okay, so we will heavily study about the inverse of the matrix very soon, and so we will see this kind of property in more detail. And at the same time, if the product AB is a zero matrix, so in that case AB is equal to 0. So in this case, it doesn't mean that A is a completely zero matrix or B is completely zero matrix. Okay, so it is not generally true. Okay, so that is also because we cannot easily divide it by A, right? So there is no notion of dividing some expression by a particular matrix. Okay, so no division is possible by matrix. Okay. All right. Then let's briefly discuss about this situation where, I mean, when let's discuss about the situation where this guy is true, but A or B, at least one of them is non-zero matrix. Okay, can we give some example corresponding to this situation? So product of the two matrices are 0, but at least one of them is actually non-zero matrix. Okay, so so in this case, so let's think of the matrix A as this 2 by 3 matrix, and maybe 3 by 4. Okay, so let's think of this product of these two matrices are completely a zero matrix. And then at least, let's think of the size of the matrix of this zero matrix. So of course, so it's 2 by 3 and 3 by 4, and so the result will be this guy, 2 by 4, right? And then all of them are 0, right? So this is a zero matrix. Okay, so let's think of this this expression in more detail. So let's consider the first column, the first 0 column of our zero matrix. Okay, so what will form this zero matrix? So in that case, we have a matrix A, so we have a matrix B, and let's consider this B1 and B2, B3, B4 as 4 columns forming our matrix B. Okay, and then we know that we know the column combination perspective. So the base columns are provided in A, right? And then the first column of B will work as a linear combination coefficient, and then that will produce the first column, right? And then accordingly, the second column of B will form the second column of the resulting matrix. Okay, and then can we let me rewrite this guy into four different expressions. A B1 is equal to 0, AB2 is equal to 0, AB3 is equal to 0, AB4 is equal to 0, right? So these four sets of a linear system is equivalent to the single equation of AB is equal to 0, right? So they are basically the same thing. Okay, so in this case, let's suppose between A and B, let's suppose B is not actually a zero matrix, because we want to make some example that satisfies this guy. The product is 0, but one of them is non-zero. But let's suppose B is actually non-zero matrix. Okay, but this assumption is not losing any kind of generalization, because if A were zero matrix, and then let's just apply the transpose of it, and then AB is equal to 0, and this A was actually non-zero one, and then we transpose it, and then B transpose and A transpose is a 0 transpose, which is a 0, and thus A is non-zero, and then A transpose is non-zero, right? So assuming the right matrix is non-zero, it doesn't lose any kind of generalization of our proof, right? Although we do not actually do some rigorous proof, but we only want to think of the some plausible or reasonable example that correspond to this situation. Okay, so let's suppose B is non-zero. Okay, and then it means among 4 different columns of B, at least one of them is non-zero. So suppose we have non-zero element maybe over here. Okay, so that way this matrix B is at least non-zero matrix, and thus in this case the column containing that particular non-zero entry will be non-zero column, of course, right? So in this case this guy will have non-zero vector B that satisfies this equation, which is the homogeneous linear system, right? So in this homogeneous linear system, B is non-zero one, or the non-trivial solution, or non-trivial solution exists, right? And then when can this non-trivial solution exist? What is the necessary condition, or the right? So A should have the free variable, right? So if A has a free variable, and then for these zeros, okay, and then B1, B2, and B3, and B4, so they are actually the identical linear system, or the same homogeneous linear system, right? So we can just freely choose any non-zero, non-trivial solution for our homogeneous linear system of AX is equal to 0, and if A has a linearly dependent columns or free variable, and then we can of course list up, or we can freely generate non-trivial solutions, as many as possible, right? And so any of these 4 chosen non-trivial solutions, and then we can form our matrix B, and then that way we can obtain this non-zero matrix B. Okay, so so in conclusion, so if AB is equal to 0, but A is non-zero and B is also non-zero, so in this case, in this case, if A is as long as A has a free variable, and then it doesn't need to be completely a zero matrix, right? So for example, 1, 2, 3, 4, 4, 6. So this is a linearly dependent columns, because I formed the third column as the sum of the, or addition of the previous 2 columns. So this is one particular example of having linearly dependent column, and of course this matrix is non-zero, right? So A is non-zero, and also B is non-zero, right? So if we satisfy this condition, what does that mean? The matrix A will have free variable, or have the linearly dependent columns. Okay, and then what if A has a linearly independent column, and then all the possible B's over here will be completely zero. Only possible solution will be just a zero vector, right? So in that case, our matrix B should be completely zero matrix. Okay, so in that case, we can conclude this, or in other words, if A is So if this this statement is true, and when is this statement true? That's when A has linearly independent column or no free variable, right? So that way we can see this kind of interesting equivalence between the linear independence or dependence and this kind of the solution of matrix product. I mean, this kind of equation. Any questions so far? And by the way, these are some interesting stuff to think about, right? In your brain, you are kind of doing some kind of thought experiments. So these ones are quite likely to be included in our exam. So you will it will have a high chance of seeing this kind of problems in your midterm exam or final. And by the way, we haven't discussed about the the midterm exam, but if you heard about the previous year's classes given by myself, and our midterm exam will consist of really large number of true or false questions. Okay, so almost 40 points will be formed by the true false questions, and then you can just simply T or F for each question. But here the tricky part is if you give a correct answer, and then you will get, of course, the positive point of maybe 2 points. But if you give a wrong answer, and then you will get the negative 2 points. And so for those problems that you gave correct answers for other problems, and then you will get deducted for additional 2 points from those correct answers. So in that case, if you don't give an answer, and then it will remain as just a 0 point. So +2 or 0 or -2. So that question has actually 4 points actually, right? So you can easily see that even though I make the total sum of all the scores as 100, but because of this tricky true false question that has a range of -2 to +2, right? So it is like in total, it is equivalent to having the total points as a 140. 140 points. Okay, so in that case, it's actually corresponding to the case that the true false question is more than half. I mean, so you have to very clear about this understanding of all the notions or concepts that we studied. Okay. Any questions? Yeah.
Has anybody ever received a negative score?
Yeah, almost every time. And if you get the negative score, and then I would say you will not be alone. there will be some other at least I find more than at least several, maybe 3 to 5 people will get the negative score in total. And it becomes clearer. I mean, that phenomena gets more prominent. I mean, more students get the negative score, of course, when I prepare for the difficulty exams. So, for example, I teach 4th grade courses such as a deep learning. And then last time I made it a little bit tricky, and so there were many students who got negative scores in total. Anyways, but this class is quite standard one, so if you just stick to our book and being able to solve most of the exercises in the book, and then you should be fine. Any other questions? Right? And then we can also define the power of the matrix. such as 2 to the power of 3 is like 2 times 2 times 2, right? So similarly, we can define a to the power of k, which is the k number of products of the matrix A. But in this case, yeah, in order to define this product of the power of the matrix size of this matrix A should be always a square matrix, right? So if it is not a square matrix, like 2 by 3, and then this number doesn't match, right? Right, and then a to the power of 0 is defined as identity matrix, and thus that will form just a input vector x, okay? And then also we studied about this transpose operator. Yeah, you guys know the transpose 1 2 3 4 5 6. Transpose is 1 3 5 2 4 6, right? And so each of our column is becoming our row. So that was the definition of the transpose of a matrix. And then transpose the matrix, and then also further transposing it will give us the original matrix. And then the transpose operator have a this kind of, satisfies this distributable law. And then we studied about this property, right? Then also the scalar multiple can be represented in this form. So so in this case, it is something like we have a scalar and a vector. For example, something like this, okay? So in this case, if we consider this transpose, and then so RA, and then what will be the transposed result? A transpose and R transpose, right? So in this case, what is A transpose? Of course, A transpose is this, it was originally 4 by 3, and it is 3 by 4, and then because we have to change the order between the product of these two, and although this guy is a scalar, but we can consider it as a 1 by 1 matrix, and so applying this transposition or the product of the transpose of the product, and then we have to reverse the order, and R transpose, which is the transpose the scalar, will just remain as the scalar, right? And then the scalar can be freely moved to anywhere in this product, and so we can freely move it to the left, right? So we can understand this relationship in this manner. Right, that's it for the first chapter. Any questions? Okay, then let's move to the next chapter. Right, next topic is the matrix inverse. So let's look at the definition directly. So matrix inverse is only defined for the square matrix. So it doesn't even make sense to discuss about the matrix inverse for the rectangular matrix. So again, matrix inverse is only defined for the square matrix. Right, and then the definition of this matrix inverse is as follows. So we are given the square matrix A, okay, and then its inverse matrix is such that when multiplying this on the right side of the matrix A, or the left side or the right side, multiplying in either side, it will generate the identity matrix. Okay, and of course the matrix inverse should have the same size as the original matrix. So matrix inverse is the square matrix as well. And so if we can find the matrix C that satisfies this equation, this expression, and then this matrix C is called the inverse matrix of the original matrix A. Okay, and yeah, this matrix inverse, yeah, sometimes a given square matrix may not have an inverse matrix at all, but if it has the inverse matrix, and then that inverse matrix, it will always be uniquely defined. Okay, so there can be no two different inverse for the same matrix. Okay, and then let's just briefly prove it. So suppose we have another inverse different from C for the input matrix A. So A has an inverse matrix of B and C, where B and C are different one. Okay, and when plugging B in the place of C, that will also be satisfied as well, right? And so let's start with just another matrix B, and then B times I will remain the same as the matrix B, right? And then this identity matrix, from the definition of the inverse for this C, we can plug in or replace the inverse, the identity matrix I as AC, right? And then by using associative law, we can represent it in this form, and thus we can first compute the product of B and A, and then that will be also be transformed into identity matrix by the definition of the inverse. I mean, by the condition that this matrix B is also an inverse, and so yeah, this guy, when changing C into B, so A should be identity, and so we can change it into identity, and so it will be C. And so our conclusion is B is equal to C. So even though we started from the assumption that we have a different inverse of B and C for the same matrix A, our conclusion is B should be always the same as C. So yeah, so it violates the assumption that B and C are different matrices, and so yeah, we can easily prove the inverse of a given matrix is always uniquely defined. Okay, and then the inverse matrix of a given matrix A is also represented as this A inverse. So yeah, a to the power of -1. Yeah, we don't read it like that. We read it as an A inverse. Okay, and so it has yeah. So suppose we have an X, yeah, just an X, and then let me just divide it by X. So in this case, it will be 1, right? Okay, and then in the world of a matrix, there is no division of the matrix, right? So this guy, let's rewrite it into this form. Instead of dividing it by X, we can just multiply with the reciprocal of X. Okay, so we are just talking about the scalar, where X is maybe 3. Okay, and then 3 divided by 3 is of course 1, right? But we can also represent it as 3 times 1/3 is also 1, right? And so if we change or view it as this product of these two, reciprocal of the original value, in this case, suppose we have a matrix A, and so it doesn't make sense to divide it by matrix A, right? But suppose we have another matrix that is kind of reciprocal of the original matrix, okay, similar to A inverse, okay, and in this case, similar to the case that X inverse or x to the negative power 1 or x reciprocal of x times x is equal to 1, the matrix reciprocal or the inverse matrix of an A times the original matrix A will be producing 1. But here 1 is not just a scalar, okay, in the world of matrix product, it is considered as identity matrix, right? So conceptually or intuitively, you can think of this as a reciprocal of the matrix, similar to like when multiplying it with the original matrix, it's having almost the same effect of dividing the matrix by its same matrix, okay? But yeah, there's no notion of dividing some matrix by some other matrix. So we only define this in the form of a matrix multiplication. So that way we write it, or we write the matrix inverse as A inverse. I mean, it's actually read as an A inverse. And then you guys haven't studied about this this formula for inverse matrix of 2 by 2, right? So it's time to study about this formula. So if our matrix is a 2 by 2 square matrix, okay, so 3, 4, 5, 6, okay, so its inverse matrix will be obtained as like computing or plugging in A, B, C, and D into this formula. And so 3 times 6 and 4 times 5, and we just change the order, I mean change the places or interchange this 3 and 6, and so 6 and 3. And then for these elements we just negate those two elements in the same place, so negative 4 and negative 5. Okay, so this is the formula for 2 by 2 matrix inverse, right? And then you can easily verify this is indeed an inverse of this original matrix by so suppose this matrix A and this guy is our A inverse. If you just compute A inverse and A inverse A, if you just compute this product of these two, and then you can easily verify that those two results are the same as the identity matrix, and so it satisfies the definition or the requirement for the inverse matrix. And so this formula will always give us the inverse of the 2 by 2 matrix. And also when do we have no inverse matrix? When when does there exist no inverse? That's when AD minus BC is equal to 0. Okay, so in this case, we cannot even write this representation, and thus that's when we have no inverse for the given matrix. Okay, so in this case, when is AD minus BC equal to 0? Okay, so it is, of course, AD is equal to BC, right? And then it can be represented as a kind of expression for involving the ratio. So right, so they are equivalent to each other, right? And then it can be represented as A to B is equal to C to D, right? Or let's change those two. So here we can put B over here and C over here, and thus A to C is B2, D. Okay, so if this condition is met or this condition is satisfied, and then we have no inverse. Okay, and then when do we have the same ratio between A and B and C and D? So 1, 3. Okay, so this is A and C, right? And then I'm gonna give you 4 over here. What should be the number? 12, right? Because we have to maintain the same ratio, right? Right? And then here, so in this situation is that this matrix doesn't have an inverse matrix, right? And then also interestingly, this situation can be viewed as like the two columns are linearly dependent. Okay, because if the ratio remains the same, and then the two vectors are on the along the same line, right? The span of the first vector, the second vector is completely included in the span of the previous vector, because the second vector is just a scalar multiple of the previous vector, right? And so if we have a linearly dependent columns, and then that's when we have no inverse. Okay, and also this kind of relationship holds true for even larger matrix of 3 by 3 or 4 by 4 and so on. And as we will see the equivalence, we will study in more detail about the equivalence of this linear independence and matrix inverse. No existence of a matrix inverse. So if your matrix has a linearly independent column, and then that matrix is invertible. It has an inverse. And if your matrix has linearly dependent columns, and then your matrix will have no inverse. Okay, so they are the same condition or same, yeah. And but when can we discuss about the invertibility or a matrix having inverse or not? Square matrix, right? So linear independence or dependence is defined for any rectangular matrix, including square and rectangular matrix. But invertibility of having inverse or not, that is only discussed for the square matrix. Okay. All right. Let's take a break for 10 minutes, and then let's resume at 1:09. 이거 안 내렸네.
제가 오늘 아침에 이메일을 보냈는데
네, 이름이
이현호.
그 저기 주셨죠?
네, 그거.
네, 내가 아직 그거 검토할 시간이 없었는데요.
네, 수요일에 제가.
수요일?
네, 수요일에 수업할 때 수업 끝나고 제가 서류를 이렇게.
네네네, 그래요. 네, 알았어요. 네,
감사합니다.
네. 그럼 그 전까지는 내가 할 건 없는 거예요?
네.
알았어요. 네.
주신 거.
네.
이거 설명 한번 더 해주시면 안 될까요? 원리가
네.
이해가 잘 안 돼서.
그러니까 이제 그러니까 A 곱하기 B가 0이 되면 일반적으로는 우리가 알고 있는 거는 그냥 뭐
네.
둘 중에 하나가 0이어야 된다라는 거잖아요. 그러니까 매트릭스 두 개가 곱해서 0이 나오려면 그럴 수도 있는데 그러지 않아도 되는, 그러니까 두 개 다 0이 아니어도 0을 만족할 수가 있는 경우가 존재한다는 거고요.
거기까지는 따라갔는데.
네. 그러면 이제 언제 그러면 이게 가능한 거냐? 그러니까 둘 다 0이 아닌데 곱했으면은 0이 나오는 게 언제 그럼 가능한 거냐? 이게 이제 결국은 우리가 그 컬럼별로 그렇고 그걸 아까 그렇게 쪼개면 그러면 이제 그 컬럼별로 쪼개면 이제 그게 다 호모지니어스 리니어 시스템으로 다 되는 거잖아요. 하나하나가. 그러면 그 호모지니어스 리니어 시스템에서 일단은 그 하여튼 그러니까 B가 난제로가 되려면 누군가는 하여튼 그 B1, B2, B3, B4에서 누군가는 이제 난 트리비얼 솔루션이 나와야 된다는 뜻이잖아요. 0이라는 이 뒤쪽에 그거를 생성을 함에도 네, 여긴 지금 다 0이니까
네.
지금 이 매트릭스랑 첫 번째 컬럼 곱하면 여기 첫 번째 컬럼
네.
결과 나와야 되잖아요. 그래서 요거를 이렇게 쓴 거잖아요. 근데 이게 중요한 게 이제 여기서 하여튼 누구든 이 네 개 중에 누구는 하여튼 난 트리비얼 솔루션이 되어야만 우리 매트릭스 B가 난 제로 매트릭스가 나오잖아요. 그렇죠? 그러니까 지금 여기서 하고자 하는 거는 둘 중에 하나가 0이면 그렇죠. 그러니까 좀 하이 레벨에서 내 설명을 좀 부실하게 했던 것 같은데 두 개가 곱해졌을 때 0이 나온다라고 하면 두 매트릭스 중에 최소한 하나가 0이다라고 하면 당연히 두 개 곱하면 0이 나오는 건 이건 너무나 자명해요. 근데 그러면은 두 개가 0이 아닌데도 불구하고 0이 나올 때가 하여튼 존재한다라고 이야기를 했고, 그게 그럼 언제 존재할 것이냐를 이제 이야기를 해보면 그게 곧 여기서 이제 봤던 것처럼 이게 난 트리비얼 솔루션이 존재해야지 된다는 뜻이 되고요. 네, 그렇기 때문에 그러면 어떻게 해야 되느냐? 바로 A가 건드린 게 어디 이러지? 네, 어쨌건 그래서 A가 리니얼리 디펜던트 컬럼을 가져야지, 혹은 프리 베리어블이 있어야만은 난 트리비얼 솔루션이 생기는 거잖아요. 그래서 A가 리니얼리 디펜던트 할 때 그러면 이제 B들이 난 트리비얼 솔루션이 비로소 가능하게 되고, 그래서 B를 난제로로 만들고요. 그러면 A가 그러면 리니얼리 A는 그러면 그러니까 A도 난제로인 매트릭스가 될 수 있느냐? 여기서도 지금 필요한 조건은 A가 리니얼리 디펜던트한 컬럼만 되기만 하면 되죠.
그러니까 이게 저희가 보던 AX는 0 그거 형태로
네.
봤을 때 X 대신에 B를 넣고 생각하는 거죠?
네, 맞아요. each column of B. 그래서 여기서 보면 지금 제일 쉽게는 여기가 1,
네.
1, 그리고 마이너스 1. 이러면 0이 되죠. 이게 컬럼 그 코에피션트를 쓰면 여기다 1 곱하고 여기다 마이너스 1 곱하면은 0이 되잖아요.
네네.
그러면 그냥 심플하게 2 마이너스 2, 3 마이너스 3, 4 마이너스 4 이러면은 두 개가 다 결론적으로는 난제로인 매트릭스 두 개가 나와서 결국은 합하면 0이 되잖아요. 네. 네.
두 번째 조건 설명해 주실 때
네.
만약에 A의 컬럼이 인디펜던트하면
네.
그리고 이런 경우가 있으면
네.
B는 0이다가 나오 이걸 아니죠?
그렇죠. 네, 맞아요. 맞아요.
만약 이게 이거면은 A가 0이면 이게 디펜던트한 거죠?
A가 0이면요, 그렇죠. 0 컬럼을 포함하면 무조건 이제 디펜던트 하다라고 우리가 배웠으니까, 그러면 이제 리니어리 디펜던트 한 거죠. 근데 이게 여기서 하여튼 따지고자 하는 거는 뭐냐면 그 A, B가 곱해서 0이 나오는데, 그러면은 A나 B 두 매트릭스 중에 하나가 완전히 0이면 그러면 하여튼 곱하면 0이 나오는 건 너무 당연해요. 근데 지금 여기서는 하여튼 두 개가 다 0이 아닌데도 불구하고 0을 만들어낼 수 있는가? 그럼 언제 그거를 만들어낼 수 있는가를 지금 생각을 해보고 있는 거라서. 네. 네. 어디서 자본이 생겼을까요? 아, 이게 내가 마이크를 무선 마이크를 키니까 저게 서프레스가 되네요. 참 신기하네요. 아날로그의 세계란 역시. Okay, so let's see. So here, so this part, which is placed in our denominator, is determining whether our matrix has an inverse or not, or our matrix is invertible or not. Okay, so this representation is called the determinant. Determinant. 이거를 뭐 아마 판별식이라고 부르나 뭐 그랬던 것 같아요. 정확하진 않지만, 네. So the determinant of a matrix, which indicates whether the given matrix has an inverse or not. Okay, and also we have to study about this determinant, but yeah, as announced in the syllabus, I'll ask you to study 2 additional online lectures available in YouTube, which is given by some famous professor at MIT. Okay, so that is maybe 2.5 hour long. Okay, so it's composed of 2 lectures of slightly more than 1 hour each. Okay, so I think that lecture is a really beautiful and very nicely described lecture. So yeah, please study that, and I will give a details through this email announcement. Okay, so right, and then using this invariable matrix, let's consider some linear system. So we now consider this linear system where this matrix A is invariable. So by saying this matrix is invariable, we assume that, or we presume that this matrix A is square matrix, right? And then we have A inverse, right? And then it is saying that if A is invariable, and then in terms of the existence and also the uniqueness of our solution, if our matrix A is invariable, and then the number of the solution is always 1, or the solution always exists, and also the number of solution, the solution is always unique. Okay, so this is the point of this theorem, and how we prove it is really simple. So if A is invariable, and then A inverse will exist, and then from here we can just multiply A inverse on either side, on both sides, right? And so even though it looks like some special kind of reciprocal of the matrix, but it's just some matrix. Okay, so it is just another matrix that has the same size as the matrix A. Okay, so yeah, by just multiplying some other matrix on the left of both equation or both terms, and then we obtain over here, this guy is converted into identity matrix, and identity matrix times X is just represented as a original vector x, and then A is represented A inverse times B. Okay. So this is our solution. Okay, so at least we prove that the solution exists, in at least in the form of this representation. Okay. So in this case, so given A inverse, which is a fixed matrix, and B is also another fixed vector, right? And so fixed matrix and the fixed vector, and then multiplying them together, it will lead us to just a fixed vector, right? So there is no possibility of obtaining different vectors through this particular or specific matrix vector product. Okay, so that way we can see the solution is always unique. Okay, and then the next theorem is about further details about this inverse. And so the inverse of an inverse is the original matrix A. Okay, so from from CA is identity, and also AC is identity. So for the inverse matrix of an A should satisfy both of these conditions, right? And so in this case, we can easily see that A works as an inverse when considering the input matrix as C, right? So it's really trivial, right? And so if A inverse is the inverse of A, and then A is inverse of A inverse, right? So these two are just two different matrices, and they have this parallel kind of a relationship between the two for the inverse relationships. Okay, and then also this guy A B inverse is actually, so here A and B are the square matrix, and then those square matrices are both having the inverse matrices, and then the inverse of the product of these two, and then they can be represented in this form. Okay, and then let's see, let's confirm or prove this easily. So suppose we have an A inverse as maybe D, okay, of this AB. So D is inverse of AB, okay. And then let's plug this D. Let's plug this B inverse A inverse into the place of D. Okay, and then B inverse and A inverse and AB. In this case, we can perform this multiplication first by using associative law, and then this part will be identity matrix, and so it can be cancelled out or it can be gone, and then B inverse times B is identity, right? And so we found the matrix that satisfies this guy, D times AB is equal to identity. Similarly, we can easily prove that when D is this guy, and then AB and AB and D is also identity matrix. Okay, we can easily see this guy is also true, and so B inverse and A inverse satisfies this equation and also this equation, and so we found at least one inverse of AB, right? But we know that the inverse matrix is unique, right? And so if we found at least one inverse matrix that satisfies these two, and then that will be your unique inverse matrix. Okay, so similarly, like the product of A, B, and C and its inverse will be C inverse, B inverse, and A inverse, right? But you can write this expression only when A, B, and C are all invariable. Okay, so if this is written only when each of A, B, and C have an inverse matrix. Okay. So is there any other kind of situations where we have inverse for the product of these two product of the matrices, but each of them doesn't have the inverse? Okay. So in this case, we can simply think of just a rectangular matrix like so in this case, A and B is representing, or the product of A and B will be 2 by 2 matrix, and this 2 by 2 matrix, which is the product of these two matrices, okay, so that will have an inverse, but each of A and B is not even a square matrix, so we cannot discuss about their inverse matrix, right? But what if we have the same size of a matrix, and is it possible to have the inverse matrix of the resulting product, but either of them doesn't have an inverse? Is it possible or not? Can anyone give an logical kind of proof as to let me give a conclusion first. So in this case, so if we consider only the square matrices to form our product, okay, in this case it is impossible to have the inverse of this guy by using non-invariable matrices. Okay, so in order to have the inverse of that product, and then each of these two matrices should be invariable. Why is it so? So in this particular case, so if you understood the previous example of having like this guy, right? Related to that, I mentioned that invariability is the same as linear independence. So linearly dependent columns will have no inverse matrix, and linearly independent columns will have inverse matrix. I mean, only for the square matrix. Okay, so we saw that kind of thing in this ratio example, right? Although we haven't proved it, but we have such an understanding about it. So by applying that, suppose the first matrix A is not invariable, and what does that mean? The columns of them will be linearly dependent. Okay, so how about this column? How is this column obtained? So this column is obtained as a linear combination of these two green columns by using the linear combination coefficient shown over here, right? And so two linearly dependent columns, and then linearly combining them, and then that will form the first column, and then another linear combination coefficient will form another column over here, right? So using the two already linearly dependent columns, and then linearly combining them, and then we produced two columns, and then those two columns will be always linearly dependent, right? And then what if we just extend it or generalize it into larger matrix cases? So now suppose we have 3 by 3 column, 3 by 3 matrix. So the product of the two 3 by 3 square matrix produces one single 3 by 3 matrix, right? So we have these 3 columns, right? And so suppose this guy is linearly dependent, so that is not invariable. Okay, in that case, can we achieve this matrix as invariable matrix? Okay, so the same analogy can be applied. So over here, so we have 3 columns and they are linearly dependent because this is not invariable matrix, right? All right, and then using these 3 columns, we have to produce also the same number of columns, right? Same number of these 3 columns, right? So using linearly dependent column, 3 linearly dependent columns, can we generate 3 linearly independent columns? Okay, in other words, 3 linearly dependent columns. Okay, and then linearly combining them using this set of coefficients, and then produce the first one, and then another set of linear combination coefficients to produce the second one, and so on. Okay, so each of these 3 columns will be linear combination of these 3 columns, and 3 columns are linearly dependent one. And then we generated 3 columns by using the linear combination of these, and then there is no way to generate 3 linearly independent columns from the linear combination of 3 linearly dependent columns, right? So it's like in more detail, if they are linearly dependent, and then something like this, right? So two of them are linearly dependent, but the third one is a linearly dependent one that forms only like a plane as a span, right? So from here, we are basically choosing any given 3 points or 3 vectors, because the span is all the collection of all the possible linear combinations of these 3 vectors, right? So choosing whatever 3 points or whatever 3 vectors from this plane, those 3 cannot be linearly independent. Okay, so that way this guy is not invariable. So if we consider the product of the square matrices, and then each of them should be linearly independent, have the linearly independent columns, and each of them should be invariable, so that the product is invariable. But is it possible that, okay, so this guy is linearly independent or invariable, but is it possible to still generate the resulting matrix as non-invariable one or linearly dependent one? So again, the question is, okay, what if this guy is linearly independent? This guy has a linearly independent columns, but the resulting matrix is having the linearly dependent column. Is it possible? Is it possible? It is possible, because so 1, 2, 3, and maybe 1, 2, 3. Okay, using the same linear combination coefficient, we produce the exact same vector in the two columns, right? And so if we just carefully choose the linear combination coefficient for generating multiple 2 or more columns, and then we can easily make linearly dependent columns, right? Right? Okay, and then regarding the last one, if A is an invariable matrix, and then A transpose, so this theorem is saying that your matrix A is invariable, and A transpose is also invariable. Okay, so that is the point. And what is the inverse of the transpose version of the original matrix? And that is the transpose of the original matrix. the inverse matrix of original matrix. So let me also explain it in more detail. Suppose matrix A is invertible, and then you have C that satisfies this, right? By the definition of the inverse matrix, right? And then now let's think of its transpose version. So for each of them, if we transpose it equally, and then they will remain the same, right? And so CA transpose is represented as A transpose and C transpose, right? And then C transpose, A transpose, and I transpose. So identity matrix and its transpose. What is that? It's just the same identity matrix, because it will only have non-zero entry along the diagonal, right? And then the transposition is doing the flipping along the diagonal axis. So no other non-zero entries in the off-diagonal part, so identity transpose is just an identity. Okay, so we suddenly found for A transpose and its inverse, right? Because by using C transpose, okay, we can satisfy this inverse, the requirement for this inverse matrix to satisfy. Okay, and then what is C transpose? It is basically the transpose of C. And what is C? C is A inverse, right? C is A inverse, and so C transpose is A inverse transpose, right? So what is that? So that is A transpose inverse, right? So what is C transpose? What's the role of it in this second expression? C transpose is the inverse of A transpose, right? So A transpose and its inverse, right? So that is the same as A inverse transpose, right? And so so suppose we have an 1, 2, 3, 4 as an A, and A inverse as maybe 4, 6, 7, 8. Okay, so it's clearly wrong. Okay, but I'm gonna just give you this example. Okay, and then what is A transpose? 1, 3, 2, 4, right? And then what is this inverse? It is just transposing, conveniently just transposing it as 5, 7, 6, 8. Okay. So again, here the point is, if A original matrix A is invertible, and then its transpose is also invertible, and its inverse matrix is simply the transpose of the inverse of the original matrix. Okay. So you can have some good and intuitive understanding about this. Any questions? Right, let me skip the proof, because I already explained a lot about this intuitive understanding and almost formal proofs. And now let's turn to this some important topic of this elementary matrix. So this elementary matrix is considering the Gaussian elimination. So you guys understand or remember the Gaussian elimination to convert one given matrix into echelon form and then reduced echelon form, right? And so we now study how to represent this Gaussian elimination process. I mean, each step of the Gaussian elimination process as a matrix multiplication. So let me just show the example. So we had a three types of elementary operations used in Gaussian elimination. So the first one was row replacement, and then row interchange, and row scaling. So these three are the three different types of Gaussian, the the elementary operations that we can perform in the Gaussian elimination, right? And so let's think of this matrix of maybe 1, 2, 3, 4, 5, 6, and right, let's assume that, I mean, it's a kind of random or arbitrary Gaussian elimination, but let me just give an example of row scaling. So suppose we scaled the first row by 2, 2, 4, 6, and 4, 5, 6. Okay, so our question is, can we represent this result as some matrix multiplication, or we basically denote it as E to indicate elementary matrix. So can we come up with, or can we obtain the matrix E that makes this equation? Okay, all right, so here we actually utilize the row combination perspective of a matrix multiplication. So let's consider the size. So it is 2 by 3, and of course if we perform the Gaussian elimination, the matrix size will remain the same, right? So it is of course 2 by 3. So what should be the size of the matrix E? It is of course 2 by 2 matrix, right? So it is always the square matrix that has the same size as the number of rows of original matrix for each of the row and the number of rows and columns, right? So let's just let's obtain the corresponding matrix E that performs the row scaling on the first column by the scaling factor of 2. Okay, so in this case, we studied that in the right matrix, it provides the base row matrix. Base row vector, right? And then now the first row of the left matrix is providing the linear combination coefficient to perform the linear combination of these two rows. So from here, we are basically using this guy. Okay, so from here we have 3 rows on the right matrix, and then now we have one particular set of linear combination coefficient that is associated with each of our row vectors of the right matrix, right? And then perform the linear combination, and that is our result. And then if we extend it, and then we still have 3 different rows on the right, and then the first set of the first row of the left matrix is providing the the first set of linear combination coefficient to form this first row, right? So we are just reviewing what we studied already. And then the second set of linear combination coefficient placed in the first row and the second row of the left matrix will form the second linear combination coefficient that will form the second row of our resulting matrix, right? So let's apply this perspective to this row operation, right? So this guy, can we represent it as a linear combination of these two rows? Okay, what will be the corresponding linear combination coefficient? It's 2, 0. Does it make sense? So we only needed the first row, right? So we didn't even need the second row, but for the first row we just multiplied it with 2, right? So that way we obtained the 2 times the first row. What about the second row in the resulting matrix? It remains the same, right? So what will be the corresponding linear combination coefficient? 0, right? Right? So let's generalize it. So suppose we have maybe 4 rows, and then maybe the second row was multiplied by maybe 5, okay, and then the other rows will remain the same. One, two, three, 4, but this guy, this guy is like this guy is times this guy times 5 is becoming the new third row, right? So what will be the corresponding matrix that will make them equal? What about the first row? It is just the same first row, and then what is the corresponding linear combination coefficient? Right? We haven't used any other rows of second, third, and fourth row. We only used the first row, and its linear combination coefficient is 1 to produce the same first row, right? And what about the second row? Right? And then what about the third row? 0, 0, 5, 0, and 0, 0, 0, 1, right? And then similarly, let's apply this kind of idea to row interchanges. Yeah, so let's just directly work on this abstract form. Maybe we have the 5 rows, and then the resulting matrix, let's see, maybe we interchange it, the first and the fifth row, fourth row, okay? So this is one example of row interchange, right? And now let's just form the corresponding matrix that will make this as an equal, right? What is the first row? I mean, first row in the resulting matrix. So that is coming from the fourth row of the input matrix over here, right? And then what is the linear combination coefficient? 0, 0, 0, 1, and 0. Does it make sense? That way, this guy, this guy, this guy, this guy, and this guy. So it's like it's having the effect of choosing the fourth row in the place of the first row of the resulting matrix. Okay? And then similarly, what about the second row and its corresponding linear combination coefficient? Good. What about the third one? Good. What about the fourth one? Good. Because we now choose the first row to produce fourth row in the resulting matrix. Okay, right? And then this guy, right? Now let's look into the most complicated one, or the most non-trivial one, of row replacement, right? So okay, so here, okay, so let's now choose the fifth row as the first row times 3 and add it to the fifth row to produce the resulting fifth row. Okay, so that is one example of row replacement. And then what about this linear combination coefficient, or the matrix that will be multiplied on the left? Okay, we still apply the same thing. What about the first row over here? Did first row change at all? No. So it should be 1 0 0 0 0, right? And then what about the second one? Yep. 0 0 0 1 0. Okay. And then now the fifth one is what? Yeah, as we can see, these are just a linear combination coefficient, right? Yep, right. 3 0 0 0 1. Okay. So now we can represent each of our elementary operations that we did in the Gaussian elimination as the matrix product. Okay, and then if you remember when doing the exercise or doing the homework, and then maybe you will have just written the augmented matrix and then do some row replacement, and then you wrote the second one and then do some other row replacement, other elementary operations and so on, right? So this is typical kind of pattern of the answer you would write, right, in the answer sheet. But now this kind of thing can be represented as a matrix product. So let's suppose this is an original matrix A, right? And then we will be able to obtain the corresponding matrix that is multiplied over here, corresponding to the first step of Gaussian elimination, or the elementary operation. Okay, let's denote it or enumerate it as E1, because this is first step and this is second step. And what is the result of it? This guy is corresponding to this guy, right? And then now from this matrix we will perform the second step of Gaussian elimination, or the elementary operation. So it will also have its own matrix corresponding to E2, right? And so E2, right? So altogether you maybe performed 12 different operations, and then this guy, so yeah, let's call it as B, and B will be our maybe echelon form or reduced echelon form, right? So we can maintain this equality signs across all the steps of the Gaussian elimination. Any questions so far? And then now let's study about really important part about important property of these each of these elementary matrices. So by the way, these matrices are called elementary matrices corresponding to each of our elementary operation in Gaussian elimination. Okay, and then now let's consider whether each of these elementary matrix is invertible or not. So our conclusion is that each of these, any elementary matrix, whether it is a row scaling or interchange or row replacement, all of them is always invertible. Okay, so from here, let's think of this matrix E and times A as maybe B. Okay, so in this case, if E is invertible matrix, okay, and then let's just multiply E inverse on the this side, okay, and then of course this guy is identity matrix by the definition of an inverse, and thus this guy will be A. So it means obtaining this matrix and then multiplying E inverse, if it exists, and then it should be able to convert or revert the original, this guy back to the original matrix. okay, because the resulting matrix should be the original matrix A, right? And then intuitively, can we think of such a matrix that can be multiplied over here to revert this matrix B into the original matrix A? Okay, so this guy is what's the difference between the original and this matrix? The difference is, of course, the row scaling, right? The first row was scaled by 2 from the original matrix, right? And so here, let's also imagine additional or second step of this elementary matrix or elementary operation that will move or revert this back to the original matrix. What would be the corresponding elementary matrix? So it is 1/2 and 0 and 0, 1, right? So similar to like multiplying it with 2 and then resulting matrix by times 1/2, right? And then it will give us the original row vector. And then the second one, we just bring it as it is, right? So this guy is your inverse matrix, and also we can just easily verify that we 0, 0, 1, and then you can easily see this guy is identity matrix. Okay, so this kind of row scaling is always invariable, and that inverse matrix is just simply this one of these diagonal matrix, and it's just compute the obtain the reciprocal of it. Okay, what about this row interchanges? Can we obtain also another matrix that is multiplied over here to revert this matrix back to this original matrix? So what is the intuitive process? It is still a kind of Gaussian element. It is kind of elementary operation. So we change it in this particular case, the first and the fourth row. And then how can we obtain the original matrix? We switch again. We interchange again the same set of 2 rows, right? And so this guy again is placed over here. So multiplying this guy again will give us the same matrix, right? So here it is a really interesting it gives a really interesting property. So in the case of this row interchange matrix, okay, what will be its inverse? The inverse matrix is the same one, okay? And now the most important part remains, but the time's up, so we'll have to continue this Wednesday. Okay, that's it for today, and thanks.
아까 그거 거기서요.
네.
이게 질문이 이거고
네.
거기서
네.
그래서 만약에 B가 논제로라고 가정했을 때
네.
이래도 일반성을 잃지 않는 거죠 일단.
네네네.
그래서 이게 뭐 하나 열이 하나 논제로라고 하면은 이게 논트리비얼
네.
솔루션이니까
네.
A가 프리 베리어블 가지고 그건
리니어리 디펜던트 하기만 하면 되는 거죠.
거기까지는 이해했는데 그
네.
다음에 논리가 어떻게 전개되는지.
그게 어떻게 되냐면
네.
지금 이게 하이레벨 스토리가 뭐냐면
네.
지금 A 곱하기 B가 그러니까 두 개의 매트릭스가 곱해져서 0이 나오면
네.
0이 나왔을 때는 둘 중에 하나가 0이 되면 당연히
네네네.
두 매트릭스를 곱해도 0이 나와요.
네.
그건 너무 당연해요, 그죠?
네.
근데 지금 여기서는 이게 매트릭스 두 개가 곱해졌을 때는
네.
이게 숫자가 곱해졌을 때랑 달리 특이하게도 두 개 다 난제로가 아닌 경우, 그러니까 둘 다 난제로, 미안해요. 둘 다 난제로인 경우에도 그 매트릭스를 곱하면 0이 나올 수 있다라는 그런 케이스가 존재한다라는 거를 지금 생각을 하는 거예요. 그럼 과연 그게 언제 존재할 것인가를 지금 생각을 해보면 바로 지금 여기서 본 것처럼 일단은 B도 난제로고, 그러니까 아까 일반성을 잃지 않고 뭐 둘 중에 하나가 뭐 난제로, 그거는 일단 좀 약간 어떻게 보면 잘못 얘기한 거고요.
그래요?
우리는 왜냐하면 둘 다 난제로인 상황을 우리는 생각하고 싶은 거예요. 왜냐하면 둘 중에 하나가 제로다 이미. 매트릭스가. 그러면은 두 개 곱해도 당연히 제로가 나오는 거 너무 당연한 거니까. 그러니까 둘 다 난제로인 케이스를 우리가 한번 생성해보고 싶은 거예요. 한번 생각해보고 싶은 거예요. 근데 그런 경우를 생성하려면 일단 B도 난제로여야 되는데, 그럼 B가 난제로이려면 지금 여기서 봤던 것처럼 난트리비얼 솔루션을 가져야 되기 때문에 A가 그러니까 리니어리 디펜던트 컬럼을 가지면 되잖아요. 그러면 아까 봤던 것처럼 A가 리니어리 디펜던트한 컬럼만 가지면 그러면 난제로 매트릭스로서 조건을 충분히 만족을 하는 거예요. 그러니까 예를 들면 뭐 이렇게 1, 2, 3, 4, 뭐 1, 2, 3, 4, 2 이게 잘못됐네요. 이거 뭐야 이거. 다시 보자. 이거 어떻게 된 거야? 이거 이상하게 됐네요. 이게 아니구나. 맞나? 맞구나. 맞구나. 네. 그렇죠. 네. 자, 이게 그러니까 지금 리니어리 디펜던트한 컬럼의 케이스잖아요. 그렇죠? 그러면 이제 이렇게 만들었고, 그 다음에 여기 난트리비얼 솔루션은 이 특정한 예제에서의 난트리비얼 솔루션은 이 마지막 컬럼을 내가 그냥 이거 두 개를 더해서 만든 컬럼이거든요. 그렇게 만든 거예요, 그냥 예를 들 때. 그러면 이제 여기다 1-1 하면은 이게 얘네들 다 합하면 0이 되죠. 그죠? 이게 난트리비얼 솔루션의 한 예가 돼요. 그죠? 이거를 그냥 다 그러니까 0으로 해도 되지만 그냥 뭐 그냥 2배, 3배, 뭐 4배 이렇게 해갖고 매트릭스를 만들면 결론적으로는 이것도 난제로 매트릭스, 이것도 난제로 매트릭스가 나오잖아요. 그러니까 우리는 두 개의 난제로 매트릭스를 가지고 이제 제로 매트릭스로 결과가 얻어진 거죠.
이게 난제로라는 걸 한 번만 다시 해주실 수 있어요?
이거요?
이게
요거?
이게 왜 난제로가 되는지.
이게 지금 그러니까 우리는 리니얼리 디펜던트한 컬럼을 가지면 된다라는 요 조건만 필요하잖아요. 그렇기 때문에 때문에 그런 예를 하나를 지금 만든 거죠.
이게 리니어리 디펜던트까지는 알겠는데 그게 난제로로 이어진다는 게 잘.
이건 지금 난제로잖아요.
그러니까 그냥 그런 예를 만들었다는 거예요.
네. 그러니까 그게 가능하다는 거예요.
근데 그게 항상 가능하다는 건가요?
리니얼리 디펜던트한 컬럼이면 가능하다는 거예요. 리니얼리 디펜던트한 컬럼으로 구성되어 있다라고 하면 지금 얘기했던 것처럼 이게 리니얼리 디펜던트한 난제로 매트릭스. 그 다음엔 그 뒤에 매트릭스는 난트리비얼한 솔루션으로 우리가 그렇게 쓰면 이제 난제로 매트릭스 두 개로 이제 만들 수가 있는 거니까요.
그러면 이건 제가 지금 잘못 쓴 건가요?
그래서 보자. A 이제 linearly dependent and 그러니까 A가 linearly dependent 하면 그러니까 이거일 땐 당연히 이게 만족이 되는데 이거일 때 이게 꼭 개런티 되진 않는다는 거예요. 그러니까 둘 다 난제로일 수도 있다는 거예요.
이게 지금
네.
감사합니다.
그 아까 전에